Thank you very much for being here. I would like to start just thanking the organization for having invited me to this event. I'm very, very, very glad to be here from Madrid. And as you see, this is dealing with, okay, it is not a pointer. Or yes, yes. Okay. It is about modeling, but it is a special type of modeling. It is not finite elements. So I was a little bit worried about not talking about finite elements, having worked all my life in finite elements. But at a certain moment, I saw the light. It is not so, but I started working for when a material is flowing using SPH. So this is the group that we are working on this topic. Okay, and this is what the talk is going to be about. So it is modeling, but modeling requires, first of all, to have to know what you are going to model. This is clear. So we will be talking about which are the phenomena that we would like to study. Because it is like the suites. There are models which are more suitable for a phenomenon than others. And then we'll talk about models. Talking about models is quite easy. Most of the models we are using, they are just simply force equal mass time acceleration for particles, for nodes, for whatever. The thing is that in many times to obtain the forces, you have to obtain derivatives and so, which makes the things a little bit more complicated. So we will be talking a little bit about about mathematical, SPH, and constitutive. I will be skipping some parts. And then what it is also important, it is that the models has to be useful. So we have to think not in the beauty of the model, but the application that people is going to do of it. So, for instance, if somebody is very much not sure about the parameters that he's using, cohesion, friction, it is 0.4, it is 0.3. We have done hundreds of tests. So this way in which we can introduce uncertainty and probability in our computation, it is very important. Also, I'm working in a project for a bank, and then people is interested in knowing, okay, if I invest that money, will that help with this save money? So we are dealing with cost, we are dealing with risk, vulnerability, intensity of events. And also, what happens if I have to do 1,000 simulations? Sometimes it is useful to use artificial intelligence, deep learning, and whatever. So this could help. We could be talking a little bit about that. So just to start about the phenomena we want to model, those are probably the simplest. So avalanches, it is just one phase. And in fact, it is the problem that people started to model at the beginning. So, for instance, Hutter started modeling these sort of things when using this approach of finite elements or finite differences for propagation of landslides. I have to say that what we are doing, it is not new. If you go back to glaciers, and here you have plenty, people was doing these things long before we were doing. Okay, so they were working on that long before. Then we have also, whoops, sometimes it is, okay, mud flows, it is again, even if it is water and soil, a mixture, people is not considering them as two-phase materials. However, in the case, perhaps the battery is not. Okay, seems it is dead. No, it is still alive. Okay, debris. So the talk could take more time for sure. So debris flow, it is a more demanding case because if the recipe for a debris flow, it is having soil. You see here landslides and water. So at the end, these problems finish by having very, very causing a lot of damage in regions like, for instance, in South China. We have also other more watery debris flows, and in this case I remember reading in the newspapers there was in floods, but a flood coming with these stones, it is a little bit exceptional. Then, okay, let us see if I can use the, oh, far better, I will use the keyboard. And then also we have the problem, which today is a quite important problem, of landslides into lakes because of the climate change, which is something that we have to worry about. Permafrost is disappearing. There are blocks of ice in the Andes, which are falling down into the reservoirs. And also because of us, people is, for instance, building an electric power plant in China, and then the water level is increasing, and then it could trigger avalanches into the reservoir, which consequences that are very bad. So, talking about models, here you have a view of more or less, and it is true that people, as always, has been started with the simplest cases and moved on into more complicated. Even from the beginning, people was using these 3D models and depth integrated models also. The problem with the 3D exists today that it takes a lot of time when propagating a very big avalanche or with a very big runout. Techniques there are level set, which cost a lot of effort, SPH, a material point model, which is newer. And here, the depth integrated approaches, either Eulerian or Lagrangian, has been using progressively from avalanches to flow slides to waves in reservoirs and to debris flow using two phases. Many questions. Which is the model we have to use? Well, it depends on what you want to do. If the problem is simple, use a simple model. If not, second, depth integrated, what are they? And we will see it. Depth integrated are cheaper, are faster, but I mean, it is they have to be used with together with other models. If you have a singular point. It is like when a beam you have a stress concentration, you go to finite elements to crack dynamics or whatever. And here is the same. Sometimes you are moving the avalanche, and at a certain moment you change from depth integrated to 3D, solve the problem in 3D and continue with the depth integrated. So combination of techniques, it is quite important. We will talk about this also a little bit. Well, so, this is good. Mathematical modeling, there are some questions, some concepts that are quite important. First of all, the three-dimensional model, even when the soil is saturated, which is simpler than the model is unsaturated, requires a lot of variables and also requires a lot of equations, which is what it is making them very, very expensive. The good news it is that we can move using these general equations into much simpler models. What it is the problem we find sometimes? Where is this free surface? Also, the boundary condition on the bottom. And then this is even in the simplest cases, the unknowns that we have. On the other hand, if we are using depth integrated, what we are using it is the height, this variable h that we have here, and the elevation. So the problem becomes a two-dimensional problem, and we don't have to care about where the free surface is, because we have it defined with this variable. Unknowns are less, and life is cheaper. But remember, if you have a problem which is difficult, you have to get back to the 3D problems. Good. And what are the equations? So as I'm in a department of mathematics, and I don't show an equation, I will be banned or whatever when coming back to Madrid. But anyway, life is not that difficult. If you look here, this is an avalanche which is moving, and then let us consider just one column. Force equal mass time acceleration. Which are the forces? The forces that we have here, the pressure at the sides, gravity, basal friction. And then what it is the mass? The mass of this column and the acceleration. That means that if we know these forces and the gradients, we are able to predict how this column of soil is accelerating. And this is the key of these depth integrated models. Then what we write is an equation like that. So this is the gradient of the pressure. But if you look at it, even if it looks a little bit awful, what we have, it is mass, time acceleration, equal forces, period. Now the problem, it is how to move this equation into our nodes, into the points, because we are going to use points. And of course, we need the mass conservation, which is that what it is entering, it is causing to the soil to move the surface up or not. Now, there is a lot of hocus pocus these days in these models, and there are some concepts which are important. Phases. Phases, it is the old concept that we are always using, solid and water. Then nodes. We can use one set of nodes for the mixture, or one set of nodes for the solid, other for the water, and we have to do that when the water is moving relative to the soil, which is important. Layers. If everything is homogeneous, we consider just one layer. But in some cases, we will need to use two cases. So I'm going to pass very fast about these concepts and illustrate them on how we use them in modeling. So avalanches and mud flows, one phase. We don't have to worry. Either we have unsaturated dry, air is a fluid, but it's not considered that far, and mud flows. Okay, one phase. Next could be having two phases, water and soil, interacting for water pressures. But one set of nodes, it is like what, for instance, finite element codes do, which is considering nodes with variables for water pressure and displacement, so UP formulations. But here, this is a nice approach. Then the pore water pressure that we have to use. In the case of the debris flow, situation changes because we have two phases, and now we will need two set of nodes. Again, if everything is homogeneous, it is just one single phase. Again, we may use, if we need it, pore water pressure analysis. And in the case of waves generated by a landslide, what it is important, it is that we have a column here, but in this column, we have just soil and water. The air is something that we are not considering so far. Okay. But this is the simplest approach. This is what we are doing now. But there are problems. So I just will talk about this one, the watering. So imagine that you have a debris flow, and the water is abandoning the debris flow. So what will happen, it is the water level will be moving down. So we will have something which is not homogeneous. So we will have a two-layer system. And it is important. Other cases, we are adding water to the mix and whatever. So this is just to show you the three cases where we have this problem of the watering. The first case, it is that the solid fraction can stop before the water does, and then the water is abandoning the fluid, the mass. The second, it is something that for engineers, it is important because we can use permeable walls. This sort of, not to do propaganda, grids that are just retaining big particles but leaving the water passing through. And also the basal grids which are leaving the water to abandon the soil. So these things are causing the water level to get down. And then we finish by having a desaturated part, a dry part in the column. The equations, well, for here what we have to do is to consider this, that we have two layers, and then just for the sake of representation, we will use white color for the air fraction blue for the water fraction, and solid and brown for the solid. Doesn't mean that one is on top and the others continue going down. These are the equations in their full glory. Never mind, all of them are acceleration and forces divided by mass here. So for solid and water, you can put them in the way you wish. The good thing of these Lagrangian approaches it is that they are much easier understood. And here I have included a little picture about the nodes that are used in this more general case. We have red for the soil, blue for the water, and then we have also these columns, which means that we can model pore water pressure dissipation using an extra, which is a finite different mesh at all the things. Now, force equals mass times acceleration. But forces include gradients. If we would only have direct forces like gravity, everything would be very easy. But we need interaction. And to do this interaction, we have to obtain the gradients, like in finite elements. We obtain the B matrix and all these things. Here it is a little bit more complicated. And this is the moment at what people get a little bit confused. So just to begin, SPH is a meshless method. Think of a finite element mesh without the elements. Reminds the nodes. Advantages, you can have the nodes moving around. For instance, this is one of the first cases that we studied in Italy, in Campania. Now, what I was telling you, it is that if you want somebody not to get into SPH, you show him this formula, which is a delta of Dirac there, and you say, I approximate the function in this way. They say, why do you need to approximate the function? Well, I need to approximate the function because I need to approximate the derivatives. But if this is the function with the delta, imagine what the derivatives would be looking like. So the Dirac properties, you know, if everybody is not sure about that, a point force in a beam, it is exactly this. How we can approximate this thing in a manner that we can use it? So instead of using the delta, we use this sort of umbrella, very useful today, this sort of umbrella functions, which takes into account only for this point, the points which are below the umbrella, under the umbrella. So under certain conditions, this approximation, it is correct when this function approximates the delta, the Dirac delta. So still, this is an integral approximation. Wow, this is very difficult. And then, okay, I will keep into finite elements. Good. Now, if you look at this thing, the problem is that we are interested in what it is happening in the nodes. What to do? Okay, what we do in finite elements, so we do a numerical integration. So this integral, we say it is a summation of the values at all the points multiplied by the weight, the associated area. So again, from here, things could be much simpler. And then the function, it is given by expression like that, with this is the associated volume, and here we are. Still, why do we need to define a function if we know the function? Answer, because what we really need, it is to approximate the derivatives. So this is for the case of SPH. For all of you, who are familiar with SPH, in SPH, mass is being introduced as a density times the volume, and then you play with densities, with masses, or whatever. Here, we are talking about volumes, so we are not talking about a mass, we are talking about this volume. This is the associated surface for this particular point, and this is the height. So the interesting thing it is that the mass is a volume, and then density, it is precisely this height. If you have a code, for instance, an SPH code for, I would say, for compressible flow, then it is very, very easy to change it into a depth integrated flow, which is what I did. It is just change densities by heights, and everything runs smoothly. Derivatives. So And this is the key point. For me, is the more important. So the approximation of the derivative, you use this formula. But you obtain this formula by doing some sort of integration by parts or using these Gauss theorems. The interesting thing, it is at the end, the gradient at one point, you obtain it as the contribution of all the points that are close to it multiplied by the gradient of this function, which you know. And these are the more important elements of the SPH, approximation of functions, but more important, the approximation of the gradient. They are, again, many recipes, that is one in particular. So we take the values of the function, you add them, multiply, divided by product of densities, multiply by the gradient, and hop, you have the gradient of this function. Okay, let us continue. The equations, I'm taking out the sources, the forces of gravity and friction. This is the equation that we have for solving the problem of due to the pressure. So acceleration in one point is given by this summation. So it is not difficult. Well, I am lying a little bit because you need to know which are your neighbors, okay? Good. So, for pressure evolution, okay, we can use some sort of shape functions, this sort of cosinus, which it is the way in which it was done a long time ago by Iverson. And then we did it always also for SPH. You use these functions, only one variable, which is the value at the bottom, and then you can obtain in a very easy manner the evolution of pore water pressure there. What happens? If the material is passing over a grid, then the value of the pore water pressure bloop, goes to 0. And goes to 0 means that pressure is 0 because your function is that. And this is not what it is happening in reality, because in reality what it is happening, it is that it is going like that and then coming to 0 here. So if the material is passing over the grid and has not stopped, still we will have, as soon as it passes, we will have pore water pressure changing here. What to do? Well, what we can do is to use this sort of finite difference meshes, this is a pure Lagrangian formulation, so it is immediate. So we solve it with finite difference. So you see, SPH, but SPH plus finite differences. And then we can solve this equation, and then we can add whatever thing we have. For instance, we can add extra dilatancy if, like some people say, when a material is shearing, it tries to dilate. So this is the idea. Then rheology. The rheology also very simple. Mechanism of friction. It is mechanism of basal friction is friction, of course. Cohesion, and then we have also some visco effects. Models. Most people use classical or ad hoc models, like for instance Boelmy, but could be based also on Impersina. However, what I will tell you about a problem. In all the formulations we have, the basal friction is obtained by using the gradient of the velocity. But in depth integrated problems, we have lost this profile of velocities. We only have this velocity, this average velocity. So what we have to do, it is knowing h and knowing the average velocity to obtain the basal friction. How to do it? Again, using a little lie. The little lie, it is just to say, okay, at this point, I have a steady state problem in which the velocity is constant, no acceleration, and it is an infinite slide. An infinite slope, an infinite landslide, or whatever. And then, yes, for this case, it is possible to obtain, given the velocity and the height, obtaining this friction. But remember, this is not truth. Just think if we have if this slope is horizontal, just imagine that we will be having a velocity and a height that corresponds to other slope angles. So we are approximating things in a crude manner, but we are happy with the approximation, which perhaps we are not right about it. Friction. Now, my point is that most of these properties depends on water content. So if we have a landslide with a certain water content, properties will change. So in the case of friction, it is through porosity. In the case of cohesion, there are formulas telling you, Julian, for instance, telling you how these parameters, this cohesion, and this depends on the water content, and same with viscosity. Viscosity depends on water content. Regarding the models, the classical models, it is just 1D models, tell you that the shear stress is given by the strength plus viscosity in general. And then you play with them and you obtain, using this very simple infinite landslide model, and then you can obtain laws like that. That you see here. One thing that it is interesting, it is probably, you don't need to know it, but you can obtain the velocity. If you know all the forces, you can obtain the velocity, by the way. Good. Persina models. Persina models in 1D are more or less expressed in this way. So we could say that that in the case of Persina, when the stress is higher than the strength, this is the formula we use for it. Again, the formal way of writing it, it is just the same. Ad hoc, people is using for avalanches and for debris flow this sort of Vuelmi law, which is you add viscosity, a viscosity which depends on the square of velocity. And use a Vuelmi coefficient that we have here. But other thing which is important, it is that Vuelmi coefficient, it may be assumed to depend also on porosity. So the water content. So this is interesting. And then we arrive to the experiments. So the experiments and the applications we are going to see, they are mainly to reinforce a little bit the points we have been talking about. First of all, this is a debris flow in Hong Kong. So it is a small debris flow, but the nice thing it is that they have very nice measurements, so it was possible to reproduce the thing. And the question is whether using a debris flow with two phases will require also to have pore water pressure or not. And then this is what we find. Left, it is with pore water pressure. Right, it is without it. We have our landslide, and this is the evolution a long time. You see that, of course, with pore water pressure, it is evolving faster, the runout is larger, and so. If you are not using pore water pressure, the price you have to pay, it is to say that the friction angle, it is smaller. Okay, so this is why people is using very, very small friction angle for granular materials, and it is probably because you have water and you have pore water pressure. This is the propagation of the front, space and time, and you see that they are much different. Pore water pressure, at the end, still in the case that we have pore water pressure, still there are some points in which they are dissipating. These models are interesting, are important to use when the time of consolidation, it is of the same order than the time of propagation. So this is a sort of recipe for it. Second, so we were talking about two phases, two sets of nodes, and a single layer. Let us go now for the case of two layers. So waves coming into the reservoir. This is South China. This is a slope, and here there is a pore water station. And here the approach, it is that in the near field, it is better to use SPH to get this thing entering. But for propagating a long distance, all these things, it is nice also to use another sort of code, for instance, finite elements or finite volumes or finite differences. In our case, we were using a code which is called fan wave, so it is fan wave, to model this. The near field and then the elevations in the near field. So SPH is quite okay for that. But however, if you if you want to propagate it along very long distances, the problem of SPH is that it is very expensive. So it is far better to use the other approach. Now, second thing, it is coming back to these problems that the watering I was saying. So the first thing it is, imagine that we have a problem in which the solid fraction has a high friction angle. So the material will stop and then the water will continue flowing. If you see here, the water has abandoned the domain. And here we have the porosity. So porosity, it is restricted, but then when the water abandons the domain, the solid domain, porosity, obviously, it is 1. These are two films, but we saw that they were not working. And this is another case, which is Popocatépetl volcano. The upper part is the solid fraction, and the lower part is the fluid. So fluid is abandoning. This doesn't mean that it has been observed. It has been observed in other lahars, but we have the topography of this problem, of this Popocatépetl gully, and then we study the propagation of it doing this. Permeable walls. An avalanche arriving here and a permeable wall. What it is happening, it is that the solid stops, but the water continues flowing. So what happens in the soil, it is that the soil, it is the mass is the watering, and the water is going further, which causes less damage. This is another film of the same that we have in looking. And then this is, it is not a divertimento, it is that we were working, solving a problem of a very big landslide in Tegucigalpa, and they were a slow landslide. So can we model slow landslides? Yes, but it is very expensive. Imagine you have a landslide with a time period of 1 year, 2 years. And here, the time step is of the order of seconds or less. So we have to get rid of that. And again, what is the solution? The solution is not original. It was obtained, first of all, by people doing glaciers. And then in École Centrale Polytechnique de Lausanne, Laurent Bouliet, Hutter, and so. But it is making, you assume acceleration is 0, and then you obtain the velocity at time n+1 using this an expression in which this thing takes into account the viscosity law that you are using. This is the vertical cut of this. This here you can see the landslide. Velocity of progression was something like 10 meters, something like that in 1 year. So we have only 2 sections. It is a pity. I know it is a shame, because we don't have measurements of pore water pressure. Remember, this is a very marginal quarter of Tegucigalpa, so not many things were available. And then how the landslide is propagating in 3 months. Again, propagation, so. And now let us go to one of the last examples, last cases. So imagine that I am interested in knowing the vulnerability under a scenario in which I have uncertainty of the parameters I'm using. So we use Monte Carlo for this avalanche, and here we have in the pixels. So this is the topographical grid we're using SPH, and then we can obtain the averages for in this set of 500 cases. Then average velocities in the pixels. We could obtain also the maximum values, the average intensity in the exposed asset that we are interested. And knowing the average intensity, we can obtain the average vulnerability. What it is more important, it is that we can also give not only the average, but also the standard deviation. And knowing this, we have the statistics. So if we are asked What it is the probability that the vulnerability exceeds this value in this asset? You can assume a probability distribution, for instance, a log normal, and to say to answer this question. So another thing in which we are working, which means when somebody says in which we are working, means you have more doubts than certainties. This comes from a volcano in San Salvador called El Picacho, from where there are some debris flow coming here. And it is true that at the beginning it is a solid material with solid, but perhaps it is the pore water pressure at the beginning which is triggering the landslide because of the rain. But rain is quite intense. So you have to assume that there is also water circulating around that. What it is interesting, it is that from here, this is the area in which it is deposited. If you look at the papers and the studies that were done in El Salvador, you find friction angles of 0.1, 0.05, which are very, very slow, not to say difficult to believe. And also you are adding a Buelmi coefficient. That's okay because, okay, that's fine. But what if what happens, it is that properties are changing with the addition of the water that it is being channelized around this quebrada, this gully. Well, using the one-phase model, it stops here. But using the one-phase model plus inflow, plus taking into account this change of properties with porosity, we obtain a better solution. Look, I'm not saying that it is the real thing. What I'm showing, it is the differences between including water or not. Why are we doing this? Because somebody was showing us pictures of the newspapers of this debris flow, and at the end, what was arriving to the village, to the small town, was very watery. So you look at the beginning, was very solid, and the end is very watery. So water has come, and properties obviously should have changed. And then you can obtain vulnerability. Vulnerability, you can obtain it just for one case. So this is explains a little bit why in this part of the city the buildings were destroyed. Problems that we have. The main problem it is that if you want to assess vulnerability, you have to say how the degree of damage that it was done to the houses. And if you want to do that, and you are in academy, and you are with your computer and in your office, you don't have the slightest idea that what happened. Nothing better than going there and talking to old people like me, and having a beer with them and asking them for what did you see there. This thing it is a mechanism of information which is fantastic. So this is another thing. Yes, we are doing models, but we have to talk to people. We have to go to these places. I remember in China with a professor from there, we were walking in the mountains just to see the probability of landslides triggered by earthquakes, because they were building dams. And he was sitting in little houses with old people, asking them, "Laoba, boss, could you give us our advice?" And this thing works beautifully. So this is quite important. Then, finishing. Okay, so this is another example of how we could use artificial intelligence. We were thinking about that for the Popocatépetl. So, because we were taking systems, something like 15 years ago, 20 years ago from China, to detect debris flow by low vibrations. And then you could say that with the noise, whether you have a debris flow or not, and what it is the intensity of the noise. What you don't know if it is going to arrive to the village or not. And then it is like the history of the wolf and the boy who was crying, "Wolf, wolf." If you miss two events, then the people will stay at home. So one possibility is to take a control section and to run many cases with many different conditions. So you obtain, using neural networks, a relation between the parameters that you can measure here in real time and the effects here. So you can say, if the height and the duration, the velocity that I'm measuring here are this value, this will arrive here, and the vulnerability or houses would be destroyed in 50%, which is quite okay. This can also go to surrogate models in which you use this sort of applications to put together a lot of computations that you have done. It is like investing. You invest time in storing a lot of cases, so you have. Oh, sorry, I was thinking you are showing me the red car. Okay, good. So it is yellow so far. Good. So this is the main thing. So using these things, you may measure these things here, and then to issue a sort of blowing a horn or whatever, and having designed some escape routes, people can go far, can escape. So, and this is a way in which we can use these things. Well, and this is an example that we're running, but I'm going to skip it also. And well, just to finish, because what is the model input in these cases? So these models are very complicated, are over simple, or whatever. Well, first of all, we need the topography. The better the topography model is, the better the results we will be able to provide. Elevation, gradients, we need gradients, of course. We also need curvatures, because the bottom friction depends on the centrifugal acceleration, on the centripetal, as you prefer. Physical properties, densities, porosities, rheological friction, cohesion, Bohelmi, viscosity, if you wish. We could have erosion, so you have to choose a law, you have to choose properties. Permeability or drag forces interparticles. You have also a consolidation. You may just use a consolidation time, okay? And then probability, use a probability model. And of course, you have to know the initial conditions. One nice thing about SPH in this precise context, it is that we have a SPH set of nodes. And we may have at the same time a very, very large topographical digital elevation model, which means that you may have 1 million of points, and then you may have 6,000 or 10,000 SPH nodes. So you are dividing a little bit the effort. What is the difference? The topographical grid, it is a structured mesh. So if you give me a point, I can tell you exactly which are the 4 nodes you have at close to you. So all operations at this level are very simple. And this is it. So thanks for the 5. I was a little bit worried about the velocity of translation, because I have talked much slower than I used to talk, believe it or not. And for me, this is all. So many thanks to all of you for having endured this thing. As I promised, the number of equations was not very, very high. Enough for somebody from a mathematical department to use, and open to any questions you may wish. Questions, you can do it directly in French if you prefer, or so French is okay. German, not. I'm sorry, not today, not this time still, but French without problem.